Hello, everyone. So while we're waiting, please add yourself to the attendees list in the meeting doc while we give the other people some time to join here.
The meeting for me also had the meetings not valid until I followed the person in the chat's link. I think it was Terrence.
Yeah, the README seems to be wrong.
Yeah.
Oh, okay. Sorry. Okay, we'll fix that one.
Yeah, I'm making a PR right now to fix that.
Thank you. That might be because we changed the meeting time and we have a new meeting ID now. Okay, given that we are on a pretty tight schedule today, I first of all want to check whether everybody who's planning to present is here. I've already seen Jeremy, who volunteered to talk about air-gapped and deploying to air-gapped environments, which during KubeCon was, I think, the topic that came up most frequently by different people. Okay, we have, I might pronounce your name wrong, so please apologize. Sundama from about the open app model here.
Yeah, I'm here. Yeah, Sudanma, that was pretty good actually.
Okay, good.
Yeah.
I tried my best. And who's going to present on cloud native build packs?
Joe and I. That's Terrence and Joe.
Okay, great. UK too. I have not seen Amy yet. There she is. All right, so I also created an issue for the logo for you, Amy. So if people have ideas, because we're most likely going to run out of time by the very end so that people can later on share ideas on logos. I think this is quite exciting that we're getting our own logo. So yeah, my proposal would be to jump right into the discussion about air-gapped environments. I moved this one first because there was really massive requests. We try to stick everyone to 15 minutes for the discussion. And ideally, if we have follow-up discussions, we can either do them via the mailing list or have them on a dedicated GitHub issue. We can decide whatever fits the situation better. So I think I have to stop sharing here and would like to pass over to Jeremy.
Okay, yeah, let me share real quick. If I can. Okay, does everybody see my screen?
Yeah.
Okay, great. So I'm gonna go over just like a high-level overview of air-gapped networks and not air-gapped networks so that everybody kind of has context. Show a little bit of security-related context, some concerns that you might have when doing these things. And then I'll just really quickly address how CNAB has addressed this so far, some lessons we've learned from that. And then I'll also draw on the conversation I had at KubeCon with somebody else that had done something similar with just Helm. CNAB's trying to do it a little bit more generically. So the first thing to talk about is, what is it actually an app? So we're talking about app definitions, and that's a lot. There's a lot of things in scope for this. Turns out that like you can use a lot of things. Your app definition could just be a Docker container, could be a compose file with a Docker container, could be a Helm chart, some Docker containers, could be some Terraform plus Helm plus Docker, any kind of combination of those things. Maybe some Bash scripts, many other things. So all those things together, one or more pieces of those things could be your application definition, represent your application. Like, how do you move that thing to other people, distribute that thing? So we're gonna just abstract away and just think about a box as the application. So what's a connected environment? Connected environment, something like this, where you've got location A, location B, and some network in between. This could be the same, like these could just be two clusters in the same data center, same region, whatever. They could be physically separate locations crossing the internet. But in reality, like your application in one location can go to the other location, right? Using whatever technology you're using. If you're using Helm, you could just Helm install. If you're using Customize or kubectl or whatever technology you're using, Terraform, like you can just directly target those other locations. So some security and verification things that play into this scenario. When you're doing that, generally if you're pushing containers, the registry doesn't change. You're going to reference an OCI registry from each of those installation targets. You can use signed descriptors. So like you could somehow sign your Helm chart or sign whatever thing manifest you're using. You can reference digest, so you get really good immutable references to those containers. You can use other trust mechanisms like TUF and Intoto, and you have access to the metadata servers to verify those things. You can pull from those registries, and when you do the pull, you can verify content digests. Everything just kind of works, and I think a lot of tooling is built to support this. If we think about using like a stable Helm chart repository, we've published to that. I'm going to install from that stable chart repository using Helm 2. I'm going to reference some Docker images that are in an existing OCI registry, and like there's nothing I really have to do outside of that because the tools are really built to support that. So what's an air-gapped network? The air-gapped network could be two physically separate locations where there is no network connecting them. We could think of in the DoD world, like a unclassified network and a classified network, or it could be a bunch of oil rigs or something that are, they don't have any connectivity between them. It could also be something where you've got intermittent connectivity, where sometimes location B can talk to location A, sometimes it can't, or sometimes it's really slow. Like all of these things could be air-gapped networks. As part of the stuff we've been doing with CNAB, trying to figure out what security looks like in that mechanism, we've had a lot of different people chime in with what they think air-gapped networks look like. I'm going to assume that it's the most extreme case right now. So it's this case where there's no network connectivity between those two things. And when you have this situation, a lot of the security assumptions that we had before fall away, and you end up having to distribute these things using something like a CD or physical media that can be moved back and forth. So you put your thing onto a media, then you move it to the next location. This happens a lot in, again, like the DoD world where I used to work. You work on classified and you burn some media and move it up to the higher level networks. Same thing kind of works for when you're going to ship something to a super disconnected thing like an oil rig. You can't push like you would in normal situations. And a lot of the security and verification things kind of fall apart as well. So location B may or may not have access to the registry where you've initially published everything. So you may work around that by saying, oh, I'll just Docker save and then Docker load in like a tarball and bring it across. But the Docker tooling itself doesn't preserve content digests. So like if you're going to rely on like hashes of the images, that won't actually work with the existing Docker tooling. If you have signed manifests or descriptors that reference those digests, those things will be invalidated. However, it is possible to import and export those things using some tooling that's not built into the Docker core stuff. So like an example here is this image relocation library from Pivotal. And then moving beyond just the Docker or OCI registry problem, if you're using TUF or something like that, you have to have access to the keys that were used to sign that content. And then you also have to have access to the other metadata that goes along with that. So in the case of like super disconnected network, you're not going to have any of that because obviously there's no network connectivity between that second location and wherever that TUF server may live. So how does CNAB handle that? Just a quick reference.
Mark, can you please mute yourself? Mark, we can hear all your background noise. You're obviously in the car. Can you please mute yourself? Thank you.
All right, we'll see if that fixes it. So CNAB is really a couple of things. It's the descriptor. So I mentioned descriptor a couple of times. In our case, it's this thing called a bundle.json. And in the bundle.json, in addition to the parameters and credentials and stuff, you're referencing some Docker images. One of those is the invocation image. So in the case of like the Helm chart or Terraform or those other things, we package all of those things into an invocation image. And then you also reference other application images. So if you're going to install something like WordPress, you might have a reference to like the actual WordPress container, and maybe you have a reference to something like MySQL or MariaDB that server is going to use. So those things are all referenced inside of that descriptor file. Then we have two mechanisms of representing the bundle. One is the thin bundle, and this is the case where we have a connected network. You're able to actually publish all of these things to OCI registries. And I say OCI registries because like they have to be compliant with the OCI spec fully. And then we store things like, we store the actual bundle.json in that OCI registry, and we store all of those images in the OCI registry. And then users are able to pull from that. So if we look at this scenario, let me move this out of the way. Location A, we can push to that OCI registry as we're doing our development. Maybe our CI pipeline rebuilds the bundle and publishes it to the OCI registry. And then users B, C, D, whatever, can just pull from that OCI registry and install directly. It works a lot like if you're going to just run Docker containers or run Helm charts. But in the the second way we can represent these things, go back, is what we call a thick bundle. And instead of leveraging just the OCI registry, what we actually do is build, in our case, a tarball. And inside of that tarball, we have a bundle.json. And then we have the representation of all those artifacts as they would exist in the OCI repository. So we take the bundle.json, the invocation image, and these other images, and we archive them into this file that we can then burn to a CD, burn to, or put onto a USB stick, however else we want to distribute that thing. And the interesting thing is that when we do this, because we're using that pivotal library I mentioned earlier, we're actually able to preserve the digests and bring those things across with us. So in contrast to that connected scenario, installation looks something like this. We take the bundle, archive it, put it on the CD, move it across the air gap. It gets rehydrated into that OCI registry on the other side of the air gap, and then you can just use tooling as normal. But because we were able to leverage all those conventions from OCI and just we're using existing technologies behind the scenes, we can take care of that. So again, we use Pivotal's image relocation to preserve content digests, but there are some issues with this. And that gets back to the fact that Notary in particular wasn't really built for fully disconnected. It wasn't implemented with fully disconnected scenarios in mind. You really need to have the signing keys and the metadata and able to leverage Notary in order to use the in toto stuff as well. So that's actually being addressed in the work that's being done for Notary v2. Obviously that's not done yet, but we're able to solve everything up until that problem because we're using just the OCI specification. So I can do a quick demo of Porter right now, which is a tool we have built to implement the CNAB spec. It supports doing thin bundles and thick bundles and imports and exports that you can do across air gap networks, or I can just open it up for questions now if anybody wants to just discuss things. I think the follow-on from this we should start discussing best practices for tooling in that space if people want to address air gap scenarios. I don't think a lot of things do right now. For instance, Helm doesn't. It's really just built for, I'm going to use my local environment and connect to this Kubernetes cluster, deploy things to it. At KubeCon, I actually had a discussion with someone who'd written a Helm plugin that did something very similar to this slide right here. Oops. So they actually take Helm charts and their plugin will scrape through them and look for all the images and then build something that looks kind of like this bundle.json. So it'll reference the Helm chart and then it'll also reference all of the images that are going to be used in that Helm chart. And then they do a Docker save and Docker load to build up a tarball with the Helm chart and the images in it. And they're able to ship that across air gap networks. That's the scenario they're trying to solve right now. But they do lose the ability to do any kind of content validation on those things because Docker save, Docker load doesn't preserve any of that. It's all based off of registries, and the tooling just doesn't handle that for you right now.
Hey, this is Rob from Red Hat. I just wanted to throw out there that we were thinking about this on our lifecycle manager, and it has a idea of folks, at least in their operator, declaring which related images that they've used for their what we call the operands, the actual app, and so that we can then slurp that into an offline registry and orchestrate that.
Yeah, I think that's a pretty common use case. It just doesn't seem that we've gone that route in a lot of tooling yet. It's obviously a pretty niche case, right? Like a lot of the stuff is built to work in assume normal operations of networks and stuff, but it's a good point to mention things.
Yeah, I think we have like a couple minutes left for questions, or otherwise you can do like a 2-3 minute demo, and I think we should be fine here too before we move to the next one.
Okay, yeah, let me just come over real quick. So here I've published a bundle. The way
Can you make it a bit larger?
Oh, sorry, yeah, forgot my text.
For people on laptop screens.
Yeah, let's see. Okay, does that look better?
That's good, yeah.
Okay, so what I did here was I ran this porter publish command, and that actually publishes the invocation image and then any other reference images to whatever registry you're doing, and then it rewrites the bundle descriptor itself to reference those things. What Porter does to define what a CNAB looks like is give you a manifest that is YAML, and you can reference things like those images. User to this thing called Porter DO bundle v1.0.0. So what I can do now is just install that thing, but that'll take a while because the cloud is not like instantaneous. So what I want to actually do, that's a representation of a thin bundle. I want to turn that into a thick bundle. Porter archive. So what that does is take a reference. We're going to use a tag reference. So we can do a Porter archive dash tag Jeremy Rickard Porter DO bundle v1.0.0, and then give it a file name we're going to write it out to. So we'll say SIG app. And what that'll actually do is pull all of the images down from that repository and then create an OCI layout from that data. It'll take a little while to run, but what it actually looks like behind the scenes, it's in the background, to another window. You end up with a TGZ like this. So it's creating that one right now, but if I just do a tar TVZ on this, inside of this, you can see all of the blobs that make up the image, or the images. There's actually two, the invocation image and then Spring Music application. There's the OCI layout descriptor itself, the index.json that you'd have from the OCI repository, and then the bundle.json itself. So then I can take this thing and move it across any other network that I wanted to, and then I can republish it. Most of the cases that we're working with right now obviously require registry, so we just kind of bake that into the workflow. So I can do a Porter publish again, and I can specify an archive file to read and then a tag I want to send it to. So I can say Porter publish archive, hello, and then tag. And it'll rehydrate that and basically run the reverse process. It'll use that pivotal library image relocation to take all of that data and basically just copy it into the OCI repository and preserve the digest as it goes. So you can see it's working purely off of digested references. And the cool thing is, like, it generates a file called the relocation file that you can pass in at runtime. You don't have to change any of the references in your file because the digests are the same. It's just this piece of it that changes. So you can still do all the validation against that you would do if it was the original reference. Cool. So that's pretty much the demo. It's pretty short.
Yeah.
Things take a while because of the copying, but.
Yeah, thanks for sharing this. Please also post into the agenda the link maybe to the presentation and the further on links
Yeah, sure.
for like getting started for people. And I would like to move right into the open app model presentation now.
Hey, okay, let me share my screen. Let me know when you guys can see my screen.
Yes, we can.
Perfect. Hey, so my name's Sudanva. I'm here to talk about the open app model. I think in the SIG app delivery deep dive at KubeCon, there was a mention of it from Harry. So the open app model was released a month before KubeCon. It's in close collaboration with both Microsoft and Alibaba. And really the open app model, we released it to target developers who are just looking to build apps on Kubernetes or any platform and have them build these apps without needing to worry about the infrastructure. So before I get into it, who am I? I'm a maintainer on one of the implementations of the open app model and a core contributor to the spec. I'm a program manager at Microsoft on the compute team. And just like 65% of the people, which is kind of crazy at KubeCon, I'm brand new to the ecosystem. So it was my first KubeCon there, just getting into the open source projects and how things work. So thanks for letting me come on this and do a talk. I think that's pretty great that we can just do that. So what is the open app model? The goal is that we wanted to create a spec that is completely platform agnostic, and it's meant to help define cloud native apps. And the premise is that you don't need to worry about any container infrastructure or any platform specifics. You can just focus on your apps and their dependencies. The inspiration of this was from some of the teams at Microsoft and Alibaba who work with some of the largest customers running Kubernetes or anything on Alibaba Cloud. And when we created the specification and when you look at the spec that I'll show you, it doesn't take any opinions on the implementation or the platform. So the spec is very intentionally open-ended, and we wanted to ensure that there could be multiple implementations on it and not just tied to one specific implementation. So why do we think that people will care about Ohm? Like, what are the kind of the three biggest things that stand out when people first check out Ohm? The first one is that it's application focused, and really the target here is the developer audience who are looking to build cloud native apps. We believe that for them today, there is a little bit too much of the infrastructure concepts that are exposed, and we wanted to bring it back to just focusing on apps. We started with the first one, and we kind of talked to a lot of customers about it. And one thing that we noticed very quickly was that large enterprises have separate people or separate roles. So they have separate developer teams, operation teams. So despite the spec, being completely developer focused, it's split up into different parts such that if you do have these different teams in charge of operating the app versus one team that's building the app and another team in charge of setting up the infrastructure, it doesn't prevent you from having these separation of roles. In fact, it actually promotes the separation of concerns to make it easy for these large enterprises to have teams that focus on their tasks and not kind of worry about the other tasks. But at the same time, if you have smaller teams and you have individuals who are doing both the developer and operations, it still abstracts you away from the infrastructure and makes your job of writing these apps and deploying them a lot easier. The final one is kind of future looking, and it is that we believe that as Kubernetes starts to be put on more edge devices, either via things like K3s or other things that might come up, that there will be an interest for people wanting a common application model for their cloud deployments, for their on-prem deployments, and also even tiny edge devices. One of the common themes at KubeCon was a lot of enterprises have hybrid deployments. So they'll have deployments across clouds, on-premise, and even edge devices. And a common ask was, hey, it would be great if you could have a consistent app model that spans across all these different environments. So I'm going to jump next into how it works. And I actually took out some slides on some of the actual components, but if there's time, I would love to come back to that. Cool. So the open app model splits the infrastructure and the platforms away from all of the application concerns. So if I'm a developer or an architect, I'm responsible for writing my code. Once I write my code, I author something in the spec called a component file, which describes my intent. When it comes to actually applying things like traffic management, Canary, and autoscaling, we have something called application configurations, which allows you to take a bunch of components that developers have authored, put them together in an application configuration, apply application concerns like what kind of identity you want, how you want to route traffic to it, what your upgrade strategy is, to those components. And both of these things together create the open app model. And you can take this open app model and deploy it across implementations of the open app model on any infrastructure. So the application configuration has these constructs and you request what you want, but as the developer and operator, you don't necessarily care about how it's provided to you. That's the goal or the job of the infrastructure operator. So you're asking for ingress, and this could be provided by something like, you know, Nginx or in Azure, the Azure load balancer or whatever it is. But how it's provided shouldn't be of concern to the developer or the operator. When we released it, we also released an implementation of Kubernetes on the open app model. And there were a few considerations when we released this. One was that developers wanted to still use the Kube API. So initially, actually, when we were previewing this thing, we had our own CLI tool, but there was heavy demand and pushback from a lot of the advocates that, hey, we like the Kubernetes API, so let us apply this open app YAML that you have created with these components and this app config directly to the Kubernetes cluster using kubectl. Alternatively, a lot of mature DevOps setups will have things like Helm charts, or even developers will use Helm charts. And we have intentionally made OHM compatible with things like Docker, CNAB, and Helm charts. You can even wrap an open app YAML in a Helm chart and use the Helm CLI to deploy it. When you deploy to a Kubernetes cluster, we have a project called Rudder, which is an example implementation of the spec, which understands all of the high-level constructs in the spec and translates them into Kubernetes deployments, pods, services for you. So I actually think the best way to show this off and talk about the spec is, sorry, just a chat, is to use a demo. I saw Alois had a question, and I will get to that right after this demo. So this demo, so the demo is going to show off the Service Tracker app, which is a bunch of microservices. So it's kind of split into a traditional 3-tier app. It has the Service Tracker UI, it has a bunch of APIs, and it has the data APIs. Each of these are wrapped up into components. So let's take a look at a component. So a component schematic is something that the developer would author, and they're stating their work, intent for how the component can run. They're stating the OS type of the component and all of the environment variables that are overridable. So in the case of the UI component, it needs to know the location or the URI of all of the API components. And finally, the port of the container. So if I look at the API components, there's 3 of them. There's the flights, quakes, and weather. Each of those are very similar. They're component schematics, so they have the exact same concepts in them. But that's all a component is. So once you're actually done with the components, you can apply it to the Kubernetes cluster. And I have a script that does it because I didn't want to run apply commands. So I'm just going to do that. So what this does on the Kubernetes cluster, if I do a get components, is it just creates these components. It hasn't created any pods for me. It's just made these components available for instantiation. And you'll notice that there's a rudder pod running, so it's the one that's being able to understand this. And if I do get kget CRDs, you can see that there are a bunch of extra CRDs that are available. So components on their own don't do anything special. The magic kind of happens in the app config where you create instances of these components. So you can stitch together all of the components, the UI component, the API component, and the data component, and create instances of them as the application operator, overriding the parameters that were exposed in them with ones that you want to expose, the ones that you want to run. So for example, if I were to deploy this in a particular environment, I might want certain parameters versus another environment. When it comes to instantiating these components, you might want to add things like ingress, and concepts like ingress and scaling are modeled by this concept in the spec called traits. So traits apply to a component and add operational functionality to them. So an example of a trait is a manual scaler. It's the most basic example where you specify the replicas you want. A more interesting one is ingress, where you specify, hey, this particular UI component, I need it to be exposed to the public internet via ingress. And this is the host name and path that I want. Again, you'll notice that there's no mention of how the ingress is provided, just that you need ingress and these are the parameters that you need. So if I go ahead and apply this configuration to the cluster, what it'll do is it will, let me apply it first. It's gonna go ahead and read this, and rudder that's running on the Kubernetes cluster is gonna create pods for each of the components that were in the application configuration, and it'll create them equal to the manual scaler information that was provided. It will also create the services for me. And if I look at ingress, it will create the UI trait ingress with the particular host name that I wanted. But from the perspective of the developer or the application operator, they never had to interact with the direct services or the deployments or the pod spec. They just described their application. And just to kind of top it off, actually, I can show you what it looks like if it works. So this is the UI component that I showed. When I click the refresh button, the pods might still be starting up. It's going to reach out to those APIs, which go ahead and pull data from an external service, and then it'll store all of this information in the local MongoDB component that's running on the cluster itself. And then I can just go check out the map of all the earthquake zones. So going back to the PowerPoint quickly, do I have much time left, Alois?
3 minutes, sorry.
Oh, perfect. So that's kind of a quick demo of Open App Model and its implementation rudder in action. There are implementations in the works within Ali Cloud, and if you join the mailing list, you'll see that we have some interest from other folks like Ballerina and Crossplane who are interested in some implementations. But that's just an example of one implementation of the spec. So a quick digest of what's happened, because we're a very recent community project. First is we released in October 2019 with an alpha version. This means that it's super open-ended for change still. It's in alpha. We're expecting a lot of feedback from calls like this and our community calls. In December, well, probably next week, we're gonna schedule a second release of Rudder, which is going to actually integrate with SMI. We have a community end user actually providing a logging trait that they want to implement with Rudder. And then there's a few validations that we wanted to put in Rudder. And the last thing is that it's super early days, so it is the best time to get involved and help us solve the space. I think the general consensus I got from KubeCon was that the Kubernetes itself is maturing, and SIGs like this is kind of going to be the next thing that end users are going to ask for and need as they start thinking about their apps. I can send this slide up, but the final slide just has information on how to get involved. So just some links. These are all hyperlinks, so it's best if I just share the slide, which I can do after. But yeah, thanks for letting me hop on and talk about Ohm. If you have any questions, I have myself, and there's actually a few other people from the project on the call who can also answer any questions you have. I saw there was some chat going on, so sorry I didn't respond to those.
Yeah, the chat was mostly operator related. Yeah, again, please edit just to the meeting agenda notes, the presentation. I think we have like roughly 1 minute for questions. If anybody wants to ask any questions, feel free to ask now. Otherwise, as always, feel free to start a thread also on the mailing list with people.
Yeah,
obviously to have that discussion. Maybe then one question from me. So where do you see the project moving going forward over the next 3 to 6 months so that people have an idea what's your high level idea?
Yeah, so over the next few months, the biggest thing for us is to get a couple more implementations of it. And right now we're actually working on a roadmap for the spec to a stable release. So right now the spec is in alpha. We're trying to figure out what it'll take for us to get to a 1.0 release of the specification. And then we're gonna go from there.
Okay, then we have one more presentation demo actually scheduled for the Cloud Native build packs. We already had some talk already about CNAP regarding air gapped, so I think this is a good follow-up. And yeah, I'll pass it over to you guys.
Thanks. So I'm Terrence, and with me is Joe. We both work at Heroku, and we're core members on the core team for the Cloud Native build packs project. Next slide. And so Cloud Native build packs are built on existing technology that came out of Heroku back in 2011 that allowed basically customers to build any type of application on our platform with like a single build pipeline. And so Cloud Native build packs basically take kind of the things that Heroku and Pivotal have learned from running build packs in production for the last 8 years and try to apply those things on top of container tooling and all the things that have kind of come out over the last 5 years. Next. So pretty simply, they'll take source code as input and then produce an OCI image that has layers that map logically to your application. Next slide. And so just as a quick example of like kind of input output here, if we have like a simple Node.js app that we're trying to build here, it's going to produce an OCI image where as a build pack author, you actually have a lot more manual control over the layers that come out of it. So you get to produce what actually ends up in what we call the launch layer, which is the thing that you'll push to your Docker registry that you can pull down and actually run, as well as having the ability to have these cache layers that can be separate from the launch image. And so next slide. So like on a second build, one of the nice things about this is that we can actually pull these cache layers in to speed up the build. So a good example is like if you are updating your package.json and you have to update node modules, you don't have to bust the entire node modules cache. You can just reuse the existing node modules and just update the difference. And the other nice thing is that on a second build, we actually only have to rebuild layers that have changed. And so that means you not only save time on build, but also pushing to the registry itself. Next. And so at the end, you get this OCI image that has reproducible builds. And since there's more structure around the build process and kind of the layout of the application, we can add metadata to that app. And as we've seen, have layers that map more directly and have tighter control over what those layers are that map to your application. Next slide. And so kind of taking a little bit of a step back, there's a bunch of different components in this part of this project. Kind of at the heart of it is the specification of like what build packs are and how they interact. And on the implementation side, we have this lifecycle that basically is an implementation of the specification itself. We have a lib build pack project that allows build pack authors to write build packs in Go that implements kind of the things that you need there. And then on the platform side, we have a thing that we'll be demoing called Pack, and it uses the lifecycle underneath to actually go ahead and do builds, and it's geared towards more like local development and assumes you have like Docker underneath the hood. And then we also maintain a Tecton template using that you can use with Knative that uses the lifecycle as well, that will run through kind of the whole build process. Next slide. And so I was talking about how we have the specification and how lifecycle implements it, and there's really two parts to this, the API, to the spec itself. There's a contract between the lifecycle and the build packs because it's actually running the build pack. So there's this build pack API, and since platforms like I was talking about, like Pack or Tecton, will actually go ahead and do all this running and kind of do all that stuff, there needs to be a contract between both what the lifecycle expects from the platform and vice versa. So there's this platform API as well. And so most platforms will basically take lifecycle directly. It's a Go binary, and actually go ahead and implement kind of building and running build packs using that. And I believe now Joe is going to go into a demo of what that looks like using Pack.
Yep. Let me know if this terminal is a good size or not. So as Terrence said, I'm going to demonstrate Pack, which is like a reference implementation of what we call a platform. So I'm going to run it against a simple Java application. This is just, I think it's like a Java Spring Boot, pretty standard Maven app. And so and people who are using Pack, the first thing they're going to do in most cases is run Pack build. And the first time you run Pack build, it'll ask you what build packs you want to run. We're going to use the Heroku build packs because that's where we work. And if we inspect that Heroku build packs image, it'll tell us what build packs it contains, which essentially map to the languages that it supports. So I'm going to set the that builder as my default builder so that the next time I run Pack build, it'll first download that image, and then when it runs the build pack lifecycle, it'll run with those build packs. So the first thing it does is detect that I'm using a Java application. I didn't have to tell it that or configure it. It'll install the JDK. It installs Maven, and then it runs Maven. The first time it runs Maven, it has to download the internet, has to download all my dependencies that it needs to compile the app, but it will cache these. And because the build packs are application aware, they know what Maven is, they know what artifacts Maven produces, it can intelligently cache these things. The last thing it does is determine what command can be used to run this application. So it actually inspects the POM file. Again, it kind of is application aware, and it detects that a Java main command can be used to start this. The last step in the execution is exporting an image, and you can see it adds layers for the application, the configuration, the JRE, and some other things. It also creates a cache, set of cache layers. But the final output is my image, which is essentially just an OCI image that I can run with Docker run or whatever command. So if because it already set up the entry point for me, I can just do Docker run. I can also use Docker push or Docker inspect. And if we do Docker inspect, we'll see that there's some metadata in here that's specific to build packs. This actually tells us what each of these layers contains so that we can reason about the image, and that's what gives it some of its performance capabilities. So if I run pack inspect image, it kind of reads that metadata. At a very high level, it can tell us what stack we're running on. That's essentially the operating system that we're running on top of, what version of the build pack was used to create this image, and some other things. We can also generate a bill of materials. So each build pack will write what dependencies that are included in the image, and what other components or artifacts. So the real value of build packs comes when you update your application. So I'm going to update this Java application to Java 11 just by writing a Java system properties file. And then I'm going to run pack build again. This time it's going to load my cache and the layers from my previous image so it can reuse them. But it'll reinstall the JDK. So now it's going to install Java 11. And it'll rerun Maven, but it's going to use that cache. So it's very fast. This is something that's essentially not possible with other mechanisms like Dockerfile, where updating your JDK would bust all of the layers, the cache layers beyond that, like the Maven cache. So we can get much faster builds because we understand the structure of this image. But the end result is just another tag of my image. And if I run Java version, I'll see that it's running JDK 11 this time. And the Buildpack also sets up some default Java options because it knows what the best way to run this app in a container is. But it's also possible to update our applications without even running a build if we're updating just the operating system. So the pack rebase command allows us to take those layers that are the Buildpack layers, the layers generated by a Buildpack, and sort of lift and shift them onto a new image of that operating system if there's an update. In this case, there is no update because I just ran it a moment ago. But if there was a new update, it would pull that down and then write, without actually running a Docker build, essentially just editing JSON, lift and shift those layers onto the new image. This is possible because of the ABI compatibility, and it's something that Heroku and Cloud Foundry have done in the past for many years. All right, that's the demo. I'll go back to the slides. Terrence will take it over again.
Cool. Thanks, Joe. So yeah, so when Joe is demoing Rebase, we have, layers in this app. And one of the things that you get with CloudNative Buildpacks when you build it with this OCI image is that when we did that pack and spec, we actually know kind of where the separation is between, Joe was showing the stack image and kind of the app layers. And so when we, next slide, when we're kind of patching and we have this like vulnerability in this operating system, a lot of Linux distros through LTS and other releases guarantee ABI compatibility between updates of that operating system. And so we're able to basically produce a new Docker image just for that OS, push that to a registry, and then using a pack rebase, we can basically do that lift and shift, have this new image without running a Docker build, and all we've done is basically replace the layers in that JSON file, and then now we can push that image up. And so you only ever have to do that once across like a fleet of, 500 apps. You push that OS image up one time, and then the actual rebasing of all your other applications can be relatively fast. Next. And so this is all great. We have some use cases of this in production, like Salesforce at Dreamforce last week just announced Salesforce Evergreen that is powered by CloudNative Buildpacks. You can use, at Spring 1, there was the announcement of the Azure Spring Cloud that uses KPack underneath, which is another platform that also leverages CloudNative Buildpacks. Project Riff, which is used in the Pivotal Function Services, which is like a FAS, uses CloudNative Buildpacks to kind of power how they build the images that get run in that platform. And so we definitely have a bunch of different platforms that are looking and using Buildpacks today in production. Next slide. And so CloudNative Buildpacks, hopefully that you've seen, allows you to basically use the same set of Buildpacks like Joe was showing with the Java one. Like you can bring any Java app to it, and so you're able to use a single Buildpack to kind of power different kinds of applications. So you don't have to, unlike Dockerfile, I guess, like rewrite a special Docker file for each individual application. With some of the capabilities with the caching and only replacing the layers that need to be changed, it can be fairly fast, as well as the rebase commands. We didn't show this part, but you can compose multiple Buildpacks together. So a lot of Buildpacks that used to be monolithic in kind of the old infrastructure can now be broken up into multiple smaller Buildpacks. So they can be modular and kind of combined that way. And then out of the gate, with some of these things that are being captured by these Buildpacks, with both like a pack and spec image for auditability and some of the rebase stuff, it allows you to separate kind of the developer and operator concerns. And so developers don't have to worry about kind of things that you normally would have to if you're writing stuff with Dockerfile for reducing images of kind of the operation level concerns. So next. So kind of pulling back to how this fits into the application delivery SIG. Buildpacks, we believe, fit in kind of, and with talking with Harry, like the topic 1.5 part of the delivery model that was showed off at KubeCon. Next slide. And so we believe that the actual like pack build, or like if you're doing that through Tekton or whatever, kind of fits in that like application packaging part, and then as well as Rebase being able to produce kind of new images as well there. And then the application definition, like the build packs actually describe how an application gets built. So the actual build packs themselves, we believe, fit into like the application definition part of that. So next, from the document, there was kind of this roll up that walked through like how Project X kind of works through different things here. And then if we go to the next slide, we believe build packs fit into this, where a lot of these projects expect you to have an existing image in a registry, and then does a bunch of really neat things with it. And so build packs kind of fit in that picture of solving the exact problem of like, I need to still build that image first. And so if you use this with Helm, for instance, like you can use build packs, produce that OCI image, and then you can have a Helm chart that then references that OCI image and then kind of fits into the rest of this ecosystem. Next slide. And so as part of the project itself, I've seen this slide before, but kind of deliverables really aiming for like the specification itself, a reference implementation called the lifecycle. In theory, you can write your own lifecycle as long as it follows the spec. A way for authors to build packs, and that's through the libbuildpack SDK, and then maintaining a set of kind of like local development with pack, and then also the Tekton template and potentially other ways that people can basically use build packs on their own platforms. And as part of this, you'll notice that we actually, as part of the project, don't have build packs as a deliverable. So the project itself is not producing, at least today, like build packs themselves as part of the project. But the hope is that we'll have an ecosystem where, like players like Roku, Cloud Foundry, Google, Microsoft, et cetera, will have build packs that kind of meet their needs. Next slide. And so we've had a bunch of releases, kind of just like quick status check stuff. Kind of the main things that people are interested in are mostly the lifecycle itself and pack as kind of the easiest way to get started with build packs, as seen through the demo. Next slide. We get asked about like how often do we break things, and so we've had kind of one major breaking change, but we take backwards compatibility fairly seriously. So when we were making this breaking change between lifecycle 0.3 and 0.4, with pack 0.41 that came out, we actually had it so it could be compatible with both versions of lifecycle. And so this allowed users who needed to update their build packs to support lifecycle 0.4 could do that kind of a little bit on their own schedule, not be forced to, when they update pack, like be forced to just have it break everything. So kind of had that compatibility layer. And then Buildpack is also another kind of tool we have to kind of capture some of these changes. And
yeah, so sorry to have to interrupt you here. I think we are on top of time, and I want to give Amy a couple of minutes. Can you please also post the slides, and we need to defer the follow-up discussion for the mailing list, and if there's more in-depth discussion to be had, obviously we can schedule a future meeting. I just want to give Amy quickly the chance to talk about the logo. Amy?
I'm unmuted. Can you hear me?
Yes, we can hear you now.
I just killed my headset and it was much easier. So hi, sorry about the echo. I'm just now just shouting at my computer because it's always a good time. We have a issue open. It's issue number 20, I believe. Please go in and put in your thoughts about logo, unless people want to talk about a logo here. I heard on site at KubeCon that people were considering a salmon for app delivery. I'm happy to take suggestions.
That is an interesting one. I haven't heard that one. I think right now we have the shopping cart still, right? So.
Well, so like for context, the other two SIGs that have currently got logos have focused on an animal theme. The raccoon is the SIG security one. It's very cute. And SIG storage went for a clam with a pearl inside of it. So If you want to be able to keep in the animal theme, you're totally welcome to. You're also perfectly welcome to be able to put in ideas for other things.
Yeah, so let's make this maybe an open discussion and then maybe put it for a vote. Let's try to put in the ideas until, say, the next meeting in 2 weeks from now, and then we just, maybe we already have a winner there, or otherwise we might put it out for a vote, and then we will let you know.
Oh, sure. So what we've done in the past is we've gotten ideas from like what direction we'd like to go in. I work with our designer over at CNCF to be able to give you some options. And then from there, we basically do like refinement from there. Process usually takes about like a month or so to be able to just kind of do the back and forth. So plan on being able to have this like, you know, up and running by January. But this also means that by the time we get to Amsterdam, you all will have a logo to be able to show off.
You actually bring up a very good point, because I think today the CFP ends for KubeCon Europe. So we should remind everybody here, if you still want to submit and haven't done so, I think you have a couple of hours left to submit your talks to KubeCon Europe.
Also a good note. You reminded me of a note that I was going to bring up as well. So yeah, that's it for me.
Yeah, thanks everyone. That I think was great meetings. Also loved the demos. I think that's definitely great, not just having slides, but showing live demos. Hopefully helps people. Please trigger discussions, especially on follow-ups via the mailing list. Ideally to have more discussions, and we'll meet again in 2 weeks. If you have agenda points that you want to bring up in the next meeting, please let us know. Okay, I think that's it for today. Thanks everyone.
Thank you. Bye-bye.